I mean, well, you got to have a good attitude for that. Enjoys helping her son color pictures of astronauts visiting the moon. In today's speech, she hopes to capture some of the facts and fascination that coexist in this realm. It is her second speech in presentation mastery. Please welcome to the lectern our towelless or towel-bearing Lara Margolanis. Applause, 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 applause. Look at that. Woo!
Thank you, Madam Toastmaster. Elon Musk, Jeff Bezos, Paul Allen, and Richard Branson have many things in common. Extremely large personal wealth, success with multiple businesses, and names that have become familiar in most households. In the last decade, they've all been aiming to add yet another commonality: access to space for people and small satellites. Making both human space travel and small satellites into successful businesses requires regular launches that cater to them, which is exactly what these four entrepreneurs are exploring. Access to space has historically been available to the exceptional few people and exquisite few spacecraft. Changing this paradigm is one of the challenges in creating these businesses. In order to illuminate this shift in space access capabilities, let's explore the basics of how to build a spacecraft. What are the 3 B's of building a spacecraft? Understanding these fundamentals will help us to see where space access has come from and where it might be going. Man-made spacecraft today come in a variety of shapes, sizes, and price tags. I'll define a professional grade spacecraft as something like a James Webb or a Hubble Space Telescope. It has a name you've probably heard of. It's large in size, contains a large number of instruments, and is also often called exquisite in its capabilities. I'll define a student grade spacecraft as something like a SCAT, or Solar Cell Array Tester, which was built at NPS. It has a name you've probably never heard of, at least not in terms of spacecraft. It's small in size, and it's often described as experimental in its capabilities. The main differences between these 2 grades of spacecraft are capability and price. If you desire more capability, then you'll pay a larger price. If your budget's small, then you'll have to make do with less capability. The first B of building a spacecraft is the bod. For my 6th grade PE teacher, everything was about the bod. Every class, as we're running circles around the gym, we hear, "Get that bod in shape!" For aerospace engineers, it's still about the bod, although in this case, it's a mechanical structure. In general, the larger the spacecraft body, the greater the cost, but it typically also means greater capability. Consider the professional grade James Webb Space Telescope. At approximately 21 meters by 14 meters and 6,500 kilograms, it's roughly the size of a tennis court and weighs as much as a school bus. The cost for a spacecraft this size, about $10 billion. This is how much it costs to build a professional grade spacecraft with the capability to image objects in the infrared, which is the wavelength of light where distant objects reside, such as the first galaxies that were formed in the universe. For comparison, a common size for a student grade spacecraft is a small cube, about 10 centimeters by 10 centimeters by 10 centimeters, and less than 1.3 kilograms in mass. It's roughly the size of a softball with the corners on it, and weighs about as much as 2 lunch boxes with the lunch in them. These can cost as little as $50,000. You can understand the appeal of a price tag this small to student-led experiments, and hundreds of successful missions have been performed at the university level as well as at the high school level using this size and price point. The capabilities of these spacecraft have varied from a simple beacon or beep from space to a relayed GPS signal to GoPro camera pictures. But the capabilities are growing as electronics shrink into ever smaller packages. The second B of building a spacecraft is the brain. As a mildly famous cartoon duo would say at the beginning of every episode, "Gee, brain, What are we going to do tonight? The same thing we do every night, Pinky. Try to take over the world. Although world domination is not typically part of a spacecraft's program, performing the same tasks every day is. This requires hardware and software that are sized to accommodate the desired tasks, perform them in a timely fashion, and report on them when asked. The professional grade spacecraft, such as the James Webb Space Telescope, can have multiple science instruments on board, as well as electrical, attitude control, communications, propulsion, thermal subsystems, all of which are managed and coordinated by an onboard computer that usually measures storage in the gigabits. The student grade spacecraft typically have scaled down versions of most of the previously mentioned subsystems, but commonly lack others, such as attitude control and propulsion. So their onboard computers are also scaled down and typically measure storage in megabytes. The third and final B of building a spacecraft is the beacon. Sputnik 1, which launched on October 4th, 1957, was the first artificial Earth satellite. It captured the attention of people worldwide with its now famous beacon. Spacecraft communication systems have grown in complexity and ability to transmit as well as receive since Sputnik, which was a straightforward beacon transmission produced at prescribed intervals. Professional grade spacecraft can contain multiple communication systems with multiple radios and antennas, but many of them still include a low power or backup beacon mode. Student grade spacecraft commonly rely on beacons as the primary way to locate a freshly launched satellite, and some use it as their sole communication mechanism. 62 years later, beacons are still an important part of spacecraft operations. Professional and student grade spacecraft get into space the same way, by getting a ride on a rocket, but cost can be problematic. When you spend $10 billion on one spacecraft, a $250 million ride to space is not such a big deal. But if you only spend $50,000 on your spacecraft, how does it get to space? Certainly not on its own rocket. NASA has stepped in with a student launch program called Alana that began in 2011 and continues today to give educational small spacecraft a ride to space as secondary payloads, which means that a large, expensive spacecraft has mostly paid for the rocket, and the small spacecraft get to hitchhike. What are your options if you have a large number of small spacecraft that you want to launch? Think Earth observation or internet in the sky applications, or if you're a human who wants to travel to space. Until recently, these options were limited to exquisite spacecraft and people. SpaceX, Blue Origin, Stratolaunch, Virgin Orbit, Virgin Galactic, among others, aim to change access to space by providing regular launches of small spacecraft and eventually people, providing unprecedented, inexpensive access to space. As Douglas Adams said, space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is in size as well as opportunity. Madam Tismister.